Hello everyone and welcome to Grinds Online Ireland. I'm Tara and today we're going to be covering proof by induction, but this time using the divising, so the division ones. So our question today is prove by induction that 2 is a factor of 3n minus 1 for all n greater than or equal to 1, where n is a natural number. And guys, you should remember, if it's a factor, that means we can rewrite it as the number 2 multiplied by a, where a is some natural number. Because then if it's a factor, we can divide by 2 and get a natural number back. That's what it means to be a factor. So in this case, we have to prove that 3 to the power of n minus 1 is equal to 2a basically. And as usual, our first part in induction is show it's equal to the smallest number. So if we substitute in 1 into this case now, we're going to get 3 to the power of 1 minus 1. That's just going to be 3 minus 1, which is equal to 2. And 2 can certainly divide by 2 and give us back a natural number 1. So we know it's true for n is greater than or equal to 1. Our next step then is going to be, we're going to assume we know it's true for some number k. So let's assume it's true for 3 to the power of k minus 1. And if we know it's true, then we know that this can be rewritten in the form 2 multiplied by a, because we know it must be a factor. And if we kind of look at that, then this might come in handy in the future. I could just bring over that minus 1 and it becomes a plus 1. So we're going to have 3 to the power of k is equal to 2a plus 1. So let's kind of keep that in mind as we go further on. Our next step is to show it's true for n is equal to k plus 1. So we need to show that when we substitute in k plus 1 into this, we're going to get a number that can be divisible by 2. So let's go ahead and substitute it in first. So if we do that, we're going to get 3 to the power of k plus 1 minus 1. And we know from our indices rules, guys, that we can rewrite 3 to the power of k plus 1 as 3 to the power of k multiplied by 3 minus 1. And looking at this equation, guys, can't we substitute in what we know for definite from part 2? We can, because we know what 3 to the power of k is. That's equal to 2a plus 1. So I can just go ahead for now and substitute that in. And we don't know what a is. A is just a natural number that we don't know. But if we substitute that in, we're going to get 2a plus 1 multiplied by 3 minus 1. And we can multiply out these two here. And if we multiply that out, we're going to get 6a plus 3 minus 1. And we can simplify that down a bit further. 6a plus 2. Now looking at that, guys, if we divide that by 2, do we get a natural number back? We do, don't we? We're going to get 3a, where a is just, again, some number we don't know, but we know it's a natural number. So a natural number multiplied by 3 must give us a natural number. And then if we're adding 2 to it, well, that's not going to make a difference whether it's a natural number or not. So we know now that 6a plus 2 is a factor of 2. But that must mean then that how we got that when we substituted k plus 1, that must also be a factor of 2. So from this, we know that it's true for n is equal to k, and we just proved that it was true for k plus 1. So our final step then in our proof by induction is stating a rolling proof is formed. Because we know it's true for k, and we know it's true for k plus 1. And k can just be any value. So for example, if k was 2, we know it's true for 3. If k was 3, we know it's true for 4, and so on. And you can go on forever and ever and ever. But from this, from showing that n is equal to k plus 1 is true, we have proved that 2 is indeed a factor of 3 to the power of n minus 1 for all n greater than 1, and n is a natural number.